So I'll talk next about the first chi-square test that we'll do in this class. It's called a chi-square test of independence. And you use this test when the outcome variable is nominal, a grouping variable, and the independent variable is nominal. So if you have, for example, two groups here, like men and women, this is your grouping variable, and then your outcome variable is nominal. So this is similar to an independent samples t-test that we're talking about, the IV here. And the example I'm going to use for this is does drinking a caffeinated beverage increase the detection of hidden objects compared to having not drank caffeinated beverages? And in this particular case, you're the participant because here is the hidden image. If you already noticed this smiley face, then you detected it. If you didn't notice this smiley face, then you failed to detect it. And so that's the outcome variable I'm going to use for this example, is whether or not somebody detected the hidden face. And the grouping variable is whether or not people had drank caffeine or not. And the null hypothesis for this test is not going to be written in mathematical language anymore. We'll just write it in regular English language. And here we'll say, for the null hypothesis, that drinking a caffeinated beverages versus decaf had no effect on detection rates. So next we'll go through the steps for a chi-square test for independence, and these will be a little different than they were for the parametric tests. We're not going to be drawing our distributions, for example. We will start off with our null hypothesis, though. And here we're looking at whether or not having drank a caffeinated beverage earlier increased the likelihood of detecting a hidden image. And so our null hypothesis is the dull hypothesis, and it says that there's no relationship between having drank caffeine and detecting the image. And then the next thing we're going to do is look at our observed data. So I'm going to create some data here and put it in a table. Let's see. So we'll say there is some people who detected the smiley face. And we'll put a miss is for people who didn't detect the smiley face. So everybody for their outcome variable is either going to be here or here. So this is our nominal outcome variable, our dependent variable. Say I'll put dv here above that column. And then people either drank caffeine or decaffeinated beforehand. We could call this the drink variable. And we'll say that 20 people drank caffeine and detected the smiley face, and 20 different people drank caffeine and failed to detect it, and 10 people drank decaffeinated coffee and detected the smiley face, and 30 people who drank decaffeinated failed to detect. the smiley face. So overall, you can see that the caffeine drinkers were more likely to detect the smiley face than those who drank decaf, right? Half of the people who drank caffeine detected it, where only 1 in 4 of the decaf folks detected it. But could random sampling explain this pattern of observation? So chi-square tests allow us to test that null hypothesis, that there's no relationship and that this pattern could just result from random sampling. So our second step here was, we'll say, I don't know, look at our observed data. So that's this here. All right, and the next thing we're going to do is calculate our test statistic. In this case, it's called a chi-square statistic. And I'll put its formula in here now, although we're not actually going to plug stuff into it yet. So it's the sum of our observed data minus the expected data, if the null hypothesis is true, squared, divided by what we expected if the null hypothesis is true. And we do that for each of the 4 cells that we happen to have in this particular data set. So our third step here for calculating our test statistic is to do this, but we need to figure out what our observed and what our expected are. And for those, the first step that we need to do is calculate what are called marginal frequencies. So what we have here, these 4 numbers are each in a cell. So these are frequencies, and they're cell frequencies. Marginal frequencies are at the margin. So if we wanted to figure out what the marginal frequency is for caffeine drinkers, we just add these up. There was 40 people who drank caffeine. We add these up to get the marginal frequency for our decaf. There's 40 people who drank decaffeinated coffee. How many people detected the smiley face? Well, let's add these up. That's 30. And how many people missed? 50. So these are our marginal frequencies. And if we add these up or add these up, we can get our total sample size here of 80. So of all the 80 people, 40 of them drank caffeine, right? And of those, half detected the smiley face and half didn't. And of these 80, 40 of them drank decaf. And of those 40 people, 10 detected the smiley face and 30 didn't. Right, and so these are marginal frequencies because they're at the margin of the table. Next, we're going to calculate our expected frequencies. This is expected assuming the null hypothesis is true. Right, and our null hypothesis says that drinking caffeinated versus decaffeinated coffee has no effect on whether or not you detect the hidden image. And so for this, we're going to redraw a table over here. And we'll call this our observed data. And this will be our null hypothesis expected data. All right, this is our E's in here, our expected data if the null hypothesis is true. So this will still be our DV, detected smiley face, failed to detect the smiley face. They drank people who drank caffeine or who had decaffeinated coffee. And what we're going to figure out is if the null hypothesis is true, how many people would we expect to have been in each of these cells? And what we're going to do is we're going to take our marginal frequencies and hold those the same for both our observed and expected values. And now what we're going to do is, given that there were 30 people who detected the smiley face, if caffeine had no effect, how should we expect these numbers to be distributed here? This 30 is going to be distributed across these in such a way that caffeine had no effect. And in this case, since there's equal numbers here, we'll split this equally. All right, so here, of those that detected the image, half of them go into the caffeinated, half go into the decaffeinated condition. And then for these 50 people who failed to detect the smiley face, since these are equal numbers here, these will be evenly distributed across these two conditions. If our sample sizes are unequal on the margins, things can get a little bit more complicated, but for this class, we'll keep it simple. And here, this is the kind of observations you would expect if our null hypothesis is true. So here, there's 40 people who had caffeine, 40 people who had decaf, and their likelihood of detecting or failing to detect the smiley faces are exactly the same as each other. And so that's what it would look like if the null hypothesis is true. All right, so we've got our null hypothesis, our observed data. We're in the middle of calculating our test statistic. We've got our marginal frequencies. We filled in our expected frequencies, and now we can actually calculate our chi-square. Chi-square. Okay. For calculating the chi-square, let me maybe just put a line here to separate the space off a little bit. All right, so our chi-square equals the sum of our observed frequency, observed cell frequency minus that cell's expected frequency, squared, divided by that exact same number. And we'll do that for each cell. So there's, for observed values, that's this 20, 20, 10, and 30. And the expected values are the 15, 25, 15, and 25. And these are going to be paired. So for this 20, that's caffeinated detect. The observed is 20, the caffeinated detect expected is 15. Right, so these are going to match on that way. And so what I'm going to try to do here is hopefully figure out a way to visualize that. So let's start with this 20, right? We're going to have, so this is summing across different numbers inside. There'll be 4 of these, one for each cell. So if we had a third drink condition, then we'd have 6 cells, and we'd have 6 of these things that are added, but we only have 1, 2, 3, 4, so we're going to have 4 of these, one for each of these observed values. So this first observed value is a 20. All right, and for that, we would have expected, if the null hypothesis is true, for this 20 to instead have been 15. So we're going to subtract that 15. Right, this needs to be squared, and you're going to divide it by the expected value. That's the exact same expected value. So that's this 20 right here. Maybe I'll put some little star thing by that, and that's here to help clarify those are connected. Now let's do this 10. Right, so we're going to be summing across all these, so we need to add, and we're doing the next observed value is 10. Then we have to subtract the decaf detected expected value of 15. All right, we need to square it and divide it by the exact same expected value. These are always going to be the same. So maybe I'll put a little green star by these, right? So this is for the decaf detected. We're summing, so we have to add. I'm just going to break onto another row here. And we'll do this 20 here. So this 20 is the observed value. Its expected was 25. This is the caffeinated miss. Caffeinated miss. It's observed as 20. Its expected is 25. Like always, we square them here. Divide by the expected value. And I'm going to put some little star here. Right, so that's the cell we're working with now. And then we have to add our last cell here. Maybe I'll get a different color for that even. So for this last one, we have a 30 as the observed value minus an expected value of 25 squared divided by the exact same expected value. right? And that's for this cell. This is the decaffeinated miss cell that we did that. And then to calculate our chi-square, we just finished doing the math for this. So I'm going to bring that back over here. Chi-square equals 20 minus 15, that's 5 squared, that's 25, divided by 15, plus 10 minus 15 is negative 5 squared is 25, divided by 15, plus 20 minus 25 is negative 5 squared is 25 divided by 25. And 30 minus 25 is 5 squared is 25. And that's divided by 25. All right. Chi-square equals, that's 1.67 plus 1.67 plus 1 plus 1. Our chi-square is 1, 2, 3, 4. Is equal to 5.33. Yeah. So our chi-square statistic, our test statistic for this data is 5.33. And there's no one-tail or two-tail test for a chi-square. It's always a two-tail test. And we next need to compare this with our critical value, just like we did with our all of our other inferential tests. All right, and this is going to be a chi-squared critical. And to determine this, we need to know how many degrees of freedom there are for this test. There's a formula that you could use, which is the degrees of freedom equals the number of rows minus 1 multiplied by the number of columns minus 1. And in this case, here's our data, right? We have 2 rows, detect versus miss, so 2 minus 1. And we have 2 columns, our caffeinated versus decaffeinated drink, 2 minus 1. And so 1 times 1 equals 1. There's 1 degree of freedom here. There's also maybe a more intuitive way to understand these degrees of freedom. And I'm going to try to write it out here. But the way degrees of freedom work for chi-square tests is you start off like you did over here with your marginal frequencies. Right, we got our caffeine, our decaf, our detect, and our miss. And having these marginal frequencies already set is analogous to having our sample mean already determined. And once those things are already determined, then when we go back and look at our data, we figure out our degrees of freedom there. All right, and for all the parametric tests, remember it was n minus 1, and you lost that 1 because if you had 3 scores, 1, 2, and 3, their mean is 2. And if you know a 1 and you know a 2, then because their mean is 2, you know the last one has to be a 3. That's the only thing that can fit in there, and that's the lost degree of freedom. Well, for chi-square tests, if these are your marginal frequencies, and you know if you set one of these to be 20, now, given those marginal frequencies, once we have this one thing set, then all of the other values are locked in. Because if this marginal frequency for caffeine is 40, well, this has to be a 20. That one is not free to vary. And if for our detect, if this is 20 and the marginal frequency is 30, well, this is set to be 10. It has to be a 10, otherwise you can't get a 30 here. Right? And if this is already set to be, if we know this has got to be 20 and this is 50, well, this has to be 30. That's not free to vary. Right? And you can do the same thing this way. So once this 20 is set, these three numbers are no longer free to vary, and so only one of the numbers is free to vary, and once that number is in this case, nothing else is free to vary. And so you get the same result, degrees of freedom 1, both ways. But here you can kind of think it through why it happens that way, and here you're blindly following a formula. Okay, so we got our critical value. Oh, we haven't determined our critical value. We got our degree of freedom to be 1. And like all of our other critical values, there's a table. So we got our chi-square table. And for this, we need our degrees of freedom to be 1. And it turns out for degrees of freedom to 1, with a p-value, with an alpha of 0.05, the critical chi-square statistic is 3.841. Our chi-square critical equals 3.841. Okay, we've got that figured out now. All right, like in the past, now that we have our actual chi-square test statistic, right, that was 5.33, and we have our critical value. Now we can decide whether or not to reject the null hypothesis. And here, like always, whenever our test statistic is more extreme than our critical value, we reject the null hypothesis. So here, we reject our null hypothesis. We decide our sample data is so unlikely to have come from a world like this that we're going to decide it did not come from a world like this. It came instead from a different world where caffeine enhanced the detection of hidden objects. Right? So we're going to reject our null hypothesis and interpret our findings. And the most straightforward interpretation here is like looking at the means for an independent samples t-test. For here, the interpretation is going to be that detection rates were higher for caffeinated participants than decaffeinated participants, and that's our interpretation. Caffeine boosted the detection of hidden objects. If we wanted to, we could get a little bit more precise perhaps and say, well, of all the 40 caffeine drinkers, 20 out of 40 detected the hidden object for decaf, only 10 out of 40 detected the hidden object, right? So caffeine doubled the detection rate. So that's a pretty big boost. There's even effect sizes that you could calculate that are similar to like an R squared or an eta squared, but I'm not going to talk about this in this class. But those are something that you could do if you wanted to. So that's the first kind of chi-square test, the chi-square test for independence. This independence here refers to whether or not one variable, in this case what the people drank, is independent of the other variable. In this case is whether or not people detected that image. The null hypothesis says they are independent, they're unrelated. Your research hypothesis and your alternative hypothesis will say they're dependent. That detection depends on if you've drank caffeine or not. So that's the chi-square test for independence, and you use it when you have an outcome variable that's nominal and an independent variable, a grouping variable that's also nominal.